Howdy Unite, Mr. Crouch here again with another YouTube video for you guys to work on. This lesson here is going to talk about the scientific theory behind plate tectonics, why it sort of happens, and the evidence that is there to support that theory and to help you out with your assignment. So give the video a watch, make sure you're downloading that worksheet, and let's get started. So before we start this lesson, just making sure that we're going ahead and grabbing those worksheets that are in the Year 9 classroom, so you can work through that again with the slides as we go. Alternatively, you can have a crack at the worksheet on your own without watching the video, but watching the video is going to be a lot easier. It's pretty much going to work through most of the answers for you, which is pretty awesome. So we'll start off with some revision. So reminding ourselves that there are 4 main layers of the Earth. So the first layer is going to be the crust. So that's the outermost layer. It's between 5 to 50 kilometers thick, and it hosts all of the life. So it's where we live, it's where your dog lives, your cat lives, your grandparents. All of life on Earth lives in that crustal layer. Next up, we have the mantle. So this is going to be our thickest layer in Earth. It's about 2,900 kilometers thick, and it's made of a semi-solid molten rock. So it's like not quite a liquid, not quite a solid. It's molten, which is the right word here. We've got the outer core, so that's the next layer down. That's going to be about 2,300 kilometers thick, and it's made of molten iron and nickel, and it's responsible for Earth's magnetic field. So we're not going to touch on that too much, but that's a really good thing to take note on. And then we've got the inner core. So that's the innermost layer, and it's made of solid hot iron, and it's almost 6,000 degrees. Now, you'd think that if it was 6,000 degrees, it'd be a liquid or maybe even a gas, but because there's so much pressure in the center of the Earth, it's actually a solid hot ball of iron. Now, reminding ourselves again as well from Mr. Basie's lesson last week. So the asthenosphere is the region of the upper mantle that has convection currents. So convection currents is when you've got hotter liquids or hotter temperatures or hotter gases rising up and circulating down the colder temperature liquids or solids or gases. All right, so you see this with a lot of like heating. You also see this in the Earth with these convection currents in the asthenosphere. So during this lesson, you guys are going to learn about the current scientific theories of plate tectonics. And to be successful in this lesson, you need to be able to successfully recall these current scientific theories and relate them to your chosen landform, so your plate tectonics or your volcanoes for your assessment task. So to start this off, we're going to start talking about the first kind of theory about the way that the Earth is structured, and that's called Continental Drift theory. Now, this was concocted by a guy named Alfred Wegener. So he was a German meteorologist and geophysicist. So meteorologist talking about things like the weather, and geophysicist talking about the way things move in like the Earth. So like rocks and landforms and stuff like that. Now, he proposed the idea of what's called continental drift in 1912. So a long time ago, which really means that we've been thinking about this for a while. And he proposed the idea of the supercontinent called Pangaea. Now, you guys might have heard about that earlier in your junior years, be that year 7, when you're talking about supercontinents. So Pangaea is this idea that all of the continents, or all of the countries and stuff like that, were merged into one really big supercontinent, as we can see on the right-hand side here. This is just showing you where all the countries would have slotted in. Now, his idea of continental drift was widely criticized, and it pretty much became forgotten because they thought he was silly. He thought, a lot of the scientific community thought, wow, that couldn't possibly be how the Earth, how the Earth moves and why we have mountains, or that all of those countries were once joined, they're hardly moving. So it was widely criticized, and pretty much it was just ignored and forgotten. Now, unfortunately, Alfred died, but we'll touch on that a little bit later. But 3 things to note with his theory of continental drift. So the first thing to note is that the continents fit together. So Alfred noticed that when he was looking at a map of the world, he saw that South America and Africa had a section in their shape that looked really similar to puzzle pieces. So it looked like they were able to fit into each other really, really well. And he theorized that if 2 countries can do that, why can't all of the other countries or all the other continents? He also noted that there was a lot of similar fossils at these sites, so he actually did an expedition to look at the fossils in South America near Brazil, which is on the eastern coast of South America, and he also looked at some of the fossils in Africa, and he noted that there were very similar fossils at both of those locations, even though they're separated by an entire ocean, by the Atlantic Ocean. And the third thing that he noted is that a lot of these continents had similar landforms that acted or appeared as if they flowed on from one another. So underneath like a lot of ice and stuff like that, and we can note a lot of this down in Antarctica, but they didn't discover this at the time. But there's a lot of landforms that have remained under all of that ice and snow that connect up with other continents and essentially flow on. But when they're separated, they just haven't, broken down over time. So Alfred's theory of continental drift really just sort of dissipated, and he actually passed away in 1930. Now, about 30 years later, and we'll touch on that in a second, someone actually did a little bit more research into it, and they came back to the idea of continental drift, but not exactly to that idea. So this is where the theory of plate tectonics comes in. So in 1960, so 30 years after he passed away, the idea of continental drift resurfaced, so it came back. Scientists started using some old war technology, so they were using seismometers, which were used during the war to listen in or feel for the vibrations of nuclear bombs going off. They used those seismometers to investigate earthquakes in the Earth's crustal layer. And they also used magnetometers, which in the war they would use to look in the ocean and see if they could find submarines. But they changed it to be more of a scientific method where they investigated the magnetic striping in rocks. Now we're going to touch on that in a second, but what you can see on the right hand side of the screen is actually an example of a magnetometer from back in the 1950s. Now, using these new devices, these scientific devices, they found out a few new things about for evidence that related to plate tectonics. So there's two that we're going to focus on here. So the first thing that they noticed using the seismometers was they were able to pinpoint the location of a lot of earthquakes. Now, you would think that earthquakes can happen anywhere, but that's not the case. What they noticed is that earthquakes are happening along certain trend lines, or what they now call certain plate boundaries. And they're a lot more frequent in those areas. Sure, earthquakes can happen in other places, but they noticed that the majority of those earthquakes were happening along those plate boundaries. So that was a new piece of evidence to show that plate tectonics could be a thing. And another thing that they noticed using the magnetometers was that there was striped rock formations. Now, as I mentioned at the start of the video, we know that the outer core is responsible for the magnetic field of Earth, and every 100,000 years or so, the Earth's magnetic poles actually shift. So what we currently see as the North Pole will actually become the South Pole at some point soon. And they've got a little bit of evidence that they think it might be happening now, but that's not what we're going to touch on today. What happens though is in the rocks, so there's three types of magnetic rocks. You've got iron, nickel, and one other one that I've already forgotten. Poor form as a science teacher. But you've got iron, and mostly that iron and nickel in the rocks that are forming, and when they're coming up from those ocean rifts, right, those ocean ridges that are pushing up that mantle, pushing up that magma into the ocean and solidifying it, what they notice is that depending on which way the poles are, so if north is actually north or if north is south, in this case here, it depends on the direction of those stripes. So when the magnetic field is facing one direction, all of those stripes are facing one direction, and then when it flips, they start flipping in the other direction, and they can see that through the way that those stripes are. So you don't have to know too much about that. It's just more of a content knowledge thing than anything. So using those two bits of information, in addition to what Alfred Wegener had already touched on with his continental drift theory, what they worked out is that there's roughly 20 sections called tectonic plates in which the continents ride. Now you can see on the right hand side here that we've got examples of all of these different plates here. So you can see Australia is on the left hand side and the Australian plate. North America is on the North American plate. You've got the Pacific plate, which is responsible for that ring of fire, which is where a lot of those earthquakes and volcanic activity happens. You can see like the Eurasian plate, the African plate. There's a whole heap of plates that are happening around the Earth. One cool thing to note as well is that you can see New Zealand, which is just to the right of Australia. It's actually separated by two different plates. So it's partly on the Australian plate and partly on the Pacific plate. That's part of the reason why New Zealand gets a lot of earthquakes, which is why it can be quite devastating there when they do happen. But again, that's something that you can look into in your own time. And now they move due to the convection currents in the Asthenosphere. Now, this is what Mr. Beatty touched on earlier last week. Now, it's important to note, though, that this is just a theory. Now, scientific theory doesn't come without a lot of reasoning. Like we've just seen in this video that there is a lot of reasoning behind why we think these things happen, but it's not a scientific law. Partly the reason for that is that the Earth's crust is really thick, and we haven't actually gone down to the asthenosphere and been able to test out that there are convection currents there. There's a lot of evidence for it, and we can make speculations about why we think that's going to happen, but it's just a theory for the moment because we can't properly go there and go, okay, this is exactly what's happening. This is exactly what's happening, but you know, you just have to kind of roll with it. But there's a lot of scientific evidence behind all of it. So once you've finished watching this video, if you haven't already, make sure you finish off that worksheet and submit it under your attendance in your own individual Google Classroom. Make sure as well that you're going ahead and finishing off your assignments. That assignment's going to be due Friday, so making sure you're spending the rest of this lesson working on that, finalising it and taking lots of photos, getting ready to submit it. And if you have any questions, make sure you have a chat with your teacher. So good luck Year 9, and I'll see you tomorrow for the next YouTube video lesson.